Welcome back to Calculus 3. Today we are moving to another section, 6.4, Green's theorem. It is the result for another aspect of line integrals. And remember, in the previous discussion, we have the so-called fundamental theorem of line integrals. But keep in mind, it must be for a conservative vector field. And the other aspect we are going to consider for today, it is the Green's theorem. Green's theorem. Okay. The Green's theorem says when you calculate a line integral on a simply connected region, and then what is simply connected region, and then the line integral can be converted into a double integral. Okay, still there's kind of cross partial derivative involved, dq dx minus dp dy. And then, because somewhat you consider this line integral f dot dr is p dx q dy, and then somewhat we did take a partial derivative, right? Take a derivative p and q. So accordingly, when you calculate the integral, you are going to take one round of integral and then move back to p and q. Then another round of integral moving back to the line integral. So this is in general the so-called Green's theorem. Okay. D must be a closed, simply connected region. Okay, this is a Green's theorem. Let's take a quick look how the Green's theorem would work. And suppose we want to calculate the line integral of this thing. And C, it is a rectangle, okay, moving from 1, 1 to 4, 1, then move up to 4, 5, move up, move back to 1, 5, then moving downward. And indeed, it is in the counterclockwise direction, right? Counterclockwise direction. So if you remember, if we insist with the definition to calculate the line integral, we really will have to calculate the line integral along this line segment, another line segment, the third line segment, fourth line segment. The line integral will have to be calculated on 4 line segments separately. And even though indeed it's just true, each case it's not complicated at all. But anyway, still we will have to consider 4 line integrals. Okay. And then according to the the Green's theorem, it says a line integral on a closed curve, simple connected closed curve, okay, and then it can be converted into a double integral. So this is the conversion. This is a line integral. Accordingly, the double integral, you're going to start with the partial derivative with respect to x, dq dx. And take a quick look what the dq dx is. It's 0, right? Then this part is p, dp dy. Okay, and take the difference of these two. And then let's do the actual calculation. It is from 0 minus x squared. And so we are looking at the double integral of this negative x squared over the region. This is like rectangular region. You can consider this type 1 or type 2, either way, right? So I'm just going to consider this a type 1 or dy dx. It really doesn't matter. You can interchange those two integrals. So eventually I get the answer as negative 84. This is a line integral calculated using a double integral. As I explained earlier, in general, to calculate a line integral when there are 4 pieces, basically it means there are 4 line integrals. But with the green theorem, we only need to calculate one double integral, even though in many cases it's not necessarily easy to calculate a double integral, but then somewhat it is, well, in some cases it's more efficient. It's more efficient. And another example, it is still from textbook, example 6.39, applying green theorem to calculate work. And this time we are having a force field, or yeah, the force field, it is given such. And then we are having a particle traverse circle, the particle traverse circle, x squared plus y squared equals 4. This is the equation of circle, right? In the counterclockwise direction. And starting and ending at the same point, 2 and 0. And this is a closed region, simply collected region in the counterclockwise orientation. Or yeah, it is indeed we consider this as the positive orientation. Okay, positive orientation. So we understand the work done by the force. It is always calculated as F dot dr. And using pdx qdy, that's a 4-dimensional vector. And when you use circle, you could use polar coordinates to do the actual calculation. And also, one thing I just realized here is that it may not be possible if you calculate use definition directly. It's y plus sine x dx e to the y minus x dx. It might be this is dy, pdx q dy, okay. And then you are going to replace y using polar coordinates or sine theta, and then x will be replaced with r cosine theta. So there is sine and cosine involved. So that's what I said. It really may not be possible to evaluate the definition directly. But keep in mind, this time the line integral we are considering here, it is on a closed curve. So I have little circle on the integral sign here. The circle on the integral sign, which means the line integral on a closed curve. Then, according to the green theorem, it can be calculated as a double integral by taking the partial derivative of q with respect to x minus partial derivative p with respect to y, right? Dq dx minus dp dy. And before I go further, let's take a quick look. What is dq dx? Dq dx, it's just -1, right? It's just -1. There's no more exponential term. dp dy, it is just 1. No more sine x, no more sine of sine or sine of cosine, those kind of things. Okay, so dq dx minus dp dy, it is just -2. -2. And furthermore, if you understand clearly the definition of the double integral, and indeed you could consider this as -2 times double integral of 1 over the region. Double integral 1 over the region, it is the area of the region. So this is -2. And the region we are considering here, it is circle of radius 2. That's 4 pi, the area. So it turned out to be -8 pi. But anyway, I still did all the calculation here. It turned out to be -8 pi. Okay. A double integral, it can be considered as, the line integral can be considered as the work done by a force field. Basically, when the work done by a force field, it is negative, which means mostly the motion along the curve, it is against the direction of the vector field. Against the direction of the vector field. You see, actually, this is the actual chart from the textbook. And probably you can tell we are moving the counterclockwise direction. So roughly, well, at least we can say it's not in the same direction as the force field. So overall, the work done by the force field, it is negative in this case. So mostly this is the fundamental This is the green theorem. This is the green theorem. This is the green theorem. Okay. And the other thing I just want to say here is somewhat green theorem and the fundamental theorem of line integral. They are consistent. They are consistent. Okay. Remember, at least I want to point out one aspect. This line integral we are considering in this section, it is always a line integral on a closed curve. And then when the vector field, it is conservative. Do you remember when a vector field, it is conservative? Those two cross partial derivatives are the same, right? So when you have a conservative vector field, a conservative a line integral for a conservative vector field, and then it turns out to be the double integral of 0, which is still 0. So like we discussed previously, the line integral for a conservative vector field on a closed curve, it is 0. So it is really consistent to the fundamental theorem of line integrals. Okay, this is, anyway, for now, we are doing 6.4 green theorem. I'm talking about the connection between the green theorem and the fundamental theorem of line integrals. Thank you for watching.